Welcome to Study Loop.
For this problem, on the topic of waves and sound, we are told that a rocket starting from rest travels straight up with a given constant acceleration. When the rocket is at a given height, it produces a sound that eventually reaches a monitoring station. And if we assume that the sound is emitted uniformly in all directions, the monitoring station first measures a sound intensity I, and at a later time measures an intensity 1/3 I. Now, if we are given the speed of sound on the day, we want to find the time that has elapsed between the two measurements. Now, the sound is emitted uniformly in all directions, and the sound wave spreads out uniformly over concentric spheres of radii r1, r2, r3, which are increasing as the wave propagates. Now, we'll let r1 be the radius when the measured intensity at the ground is I. We'll call this position 1 for the rocket. And r2, the radius when the measured intensity at the ground is 1/3 I. So r1 corresponds to a measurement at the ground of I, and r2 corresponds to a measurement of intensity of 1/3 I. So the time required for the energy to spread out over a radius r1 is t1, and this time t1 is equal to the radius r1 divided by the speed of sound vs. Similarly, the time required for the energy to spread out over a radius r2, we'll call it t2, and that's r2 over vs. Now, as the sound wave emitted at position 1 spreads out uniformly, the rocket continues to accelerate upward to position 2. And now we'll call the acceleration ay, and the time of the acceleration t12. And therefore, the time that elapses between the two measurements we'll call t, and t is equal to the difference in times t2 minus t1 plus the time it takes for the rocket to accelerate to position 2, t12. Now we'll call this equation 1. And now we need an equation to express t12. And t12 is the time it takes the rocket to accelerate from position 1 to position 2. So this is the change in velocity of the rocket between the two positions over the acceleration ay. So v2 is the speed of the rocket at position 2, and v1 is the speed of the rocket at position 1. Now we'll call that equation 2. So we can combine equations 1 and 2, and we get an equation for the difference in time between measurements, which is t2 minus t1 plus the expression above, v2 minus v1 over ay. And we'll call this equation, this combined equation, number 3. Now, from the data that we are given, we know that r1 is 562 meters, and we need to find r2. We know that the intensity I1 is equal to the sound power divided by a sphere of area 4 pi r1 squared. And at position 2, the intensity I2 is the same sound power developed by the rocket divided by the area of that sphere, 4 pi r2 squared. But we know that I1 is 3 times I2. So this gives us a simplification in the two equations above. So we can equate, and we get that P over 4 pi r1 squared is equal to 3 times I2, which is 3 times P over 4 pi r2 squared. And with some rearranging, we can find R2 using R1. So R2 is equal to R1 times root 3, which is equal to 562 meters times the square root of 3. So we actually find R2 to be 973 meters. And using R1 and R2, we can go back to our equations for the time. So the time T1 for the energy to spread over radius R1 is R1 over the speed of sound Vs. That's 562 meters divided by the speed of sound, which is given as 343 meters per second. This gives us a time T1 of 1.64 seconds. Similarly, T2 is R2 over the speed of sound Vs. And this is 973 meters divided by the speed of sound 343 meters per second. And so calculating, we get T2 to be 2.84 seconds. So if we take the upward direction as positive, we need to now find V1 and V2, so we can find T12. V1 is equal to the square root of 2 times the acceleration times R1. And this is using the equation, the kinematic equation, Vy squared is equal to V naught y squared plus 2ay times y. And so we rearrange this equation and we have an expression for V1. And now we have these values, so we can put them into this equation. So that's 2 times the given acceleration of 58 meters per square second, and R1 is 562 meters, which gives us the value for V1 to be 255 meters per second. So that's the speed of the rocket at position 1. And then similarly, V2 is equal to the square root of 2 times ay times R2. And this again is the square root of 2 times 58 meters per square second times 973 meters, which gives us V2. So the speed of the rocket at position 2 is 336 meters per second. Now we can put these values back into equation 3. So we have values for T1, T2, V1, and V2. So we can calculate the difference in time between the two measurements to be 2.84 seconds minus 1.64 seconds plus the difference in speeds, 336 meters per second minus 255 meters per second over the constant acceleration of the rocket, which is 58 meters per square second. And so calculating, we get the difference in time between the measurements to be 2.6 seconds.